All right, hey guys, how's it going? So today we're going to talk about linear ODEs. This is a topic that we've really already done quite a bit with, but we're going to sort of formalize a couple things with it. So first thing we need to talk about is what makes an ODE linear. And of ODE, of course, is linear if it can be written in this form, right, in some fashion, right? One important thing to note here is that these two functions of x, so you have this p of x and this r of x, they may not be linear, at least in terms of x. So these may not be linear. So for example, r of x could be something like x squared or tangent of x or something like that. It doesn't have to be linear. The idea is that y and y prime are completely linear, and that's what makes this ODE linear, right? So now, of course, it may not be presented to you right away in that form. It may be presented in a form that looks more like this, but of course, what you would do in that case is you would divide through by your f of x to make this be something like, not y equals, we would have y prime plus p of x over f of x times y is equal to r of x over f of x, and that's what we would just consider sort of as our new form, right? And then we would think of p of x over f of x is just p of x, and then r of x over f of x is just sort of our new r of x, right? So just as a quick example, you see this this equation here, right? We have y prime times cosine of x plus y times sine of x is equal to x is linear. And again, note that the cosine and the sine terms, of course, there are nonlinear functions, but that's irrelevant because they're in terms of x, and we only are concerned with the linearity in terms of y and y prime. So then this will be a linear ODE. Right. One thing that's important to note, especially in engineering applications, is that typically this non-homogeneous term, this r of x, is typically considered as input to some kind of system, and your solution y of x is therefore the response to that incoming input. So that's one thing that is particularly interesting, even in nonlinear ODEs. Okay, so first I want to talk about the non-homogeneous case, which is quite straightforward. And in fact, this is something that we've already done a handful of times. And in fact, if I write it this way, so if I think of my y prime as dy dx, and I'm just going to write p of x as p for now, and we have p times y is equal to 0. Of course, what can you do there? Well, we can think of this as dy dx is equal to negative p times y. And then, of course, once you move your stuff around, this is a separable differential equation. So we can think of this as dy over y is equal to negative p dx, right? So, of course, now we can integrate both sides. So if we integrate both sides, we'll then get ln of y is equal to negative whatever the integral of p of x, let me put my x back here, d of x, right? So I'm not just tacking on an x, p is some function of x. And of course we can now say by exponentiating that we would get that y is equal to whatever e to the negative integral of p of x dx is, right? And I guess technically we should have some constant c in there as well, right? So the homogeneous case is something that we've already done quite a few times already, and that's how you could find your general solution for the homogeneous case. So we're not going to do an explicit example of that just because we've sort of have looked at separation of variables quite a bit already. So what I'm more interested in is the non-homogeneous case, right? So now what if you have your r of x instead of, in this case, this r of x we're now considering not equal to 0. So making this now the non-homogeneous case. So now sort of the idea here is that we're going to use integrating factors, right? So what I need to do is I need to multiply everything by some function f, right? That way that I can express now my left-hand side. If we look a little closer, we can think of this almost as sort of like a product rule. As long as this fp, if that's f prime, then we exactly have a product rule here, right? So that's what we're going to sort of assume to be true here. So we're going to assume that our f prime is equal to my p of x times f, right? So if we now consider that and we convert this to a separable differential equation, well, moving the f over, and you write our f prime as df dx and slide your dx over and integrate on both sides, we get that the natural log of f is equal to the integral of p dx. And you can find that your f would then therefore have to be e to the integral of p of x with respect to x, right? So now once we take our integrating factor and we plug it into our equation here, right? So we've replaced f, right? If you just remember before, this was f y prime, and then this was p times f times y, and this, of course, we said was our f prime, right? That's exactly what we have here in the red, right? And that's what's equal to our r of x times our integrating factor again. Now, we can say that this, by the product rule, is the derivative of e to the integral of p with respect to x times y, and then by integrating on both sides, we sort of get this double integral here in the e term, but we have that this left side, basically we just got rid of the prime, and on the right side we integrated with respect to x, right? So now all that remains to be done is divide your e to the integral of p with respect to x over, and then you get your general solution of the non-homogeneous case, right? So that's what we have when all is said and done down here. Right, so let's look at a quick example. So the example that I want to look at is we want to solve the linear ODE y prime plus y tangent of x is equal to sine of 2x with the initial condition of y of 0 is equal to 1. Okay, so again, same idea as sort of the derivation of this. So we want to think of our y tangent, or sorry, just our tangent of x as our p of x, and our sine of 2x is r of x. And it may be helpful later, we'll just put this just for now, just in case, but it may come in handy later that sine of 2x is equal to 2 sine of x times cosine of x, right? So we've already proved it. We've already done the hard work. Let's not go crazy here. But our integrating factor, again, is e to the integral of p with respect to x. So our integral of p with respect to x in this case is the integral of tangent with respect to x. And if you're not familiar, this one can be done using substitution. Right? If you think of this as sine over cosine, then let your u be cosine. And then your du would then be a negative sine of x dx. So then we can think of this new integral, once we make our substitution, as the integral minus out front from our du. This is 1 over u du, which is a negative ln of u, which we can think of as negative ln of cosine of x, which we can also think of as ln of 1 over cosine of x. So this is a ln of secant of x finally. Right? So now remember, we did all that so that we could get this integrating factor here. So now we know that this is e to the integral of p with respect to x, which we just found was ln of secant of x. So of course, e and ln undo each other, and we get a secant of x here. right? So now when I multiply through my original equation by my integrating factor, right? So the original equation was y prime, let's see here, plus a y times tangent of x, and then that equaled the sine of 2x, right? Which we may or may not use the other form for. And if, you know, you're sort of clever, we might see that that's definitely going to be the way we want to think of it. So if I now multiply through by my secant of x, right, well, now what do we have? Well, this is secant of x, y prime, and then this is y. I'm just going to leave this left side alone for now, right? But if we look at the right side, we can say this is 2 sine x cosine x, and secant is 1 over cosine. So those cosines are going to cancel, and we're going to get that this right side is just a 2 sine of x. All right. Now remember that our solution is going to be y is equal to 1 over e to our integral of p of x with respect to x, and then that's all getting multiplied by the integral of r of x times e to the integral of p with respect to x plus c. So now we just need to plug in everything, right? So what we have is that we know that our e to the integral of p of x was a secant of x, right, which we can fix in a second. And then our r of x was what we did up here. So that just ends up being a 2 sine of x. And then our e to the px dx again was our secant of x. And then plus c. Right? Well, again, I need to slide a dx in there. Right? So again, sine times secant is a sine over cosine, so that's going to end up being a 2 and then a tangent of x dx plus c, right? And I can think of 1 over secant as a cosine of x, right? So now I need to, let me just make sure that we're all good here. So I believe, yeah, so we had tangent of x, we had sine 2x. Okay, I think everything looks good here. So now when I integrate my tangent of 2x, I believe we're going to get what? So let's see. I actually think, am I missing something here? So let me see for a second. So this is definitely the right solution form. Let's see. Let's see. Oh, I already multiplied by the secant, right? So I actually don't need this secant here. Yeah, that's what I'm doing wrong. Okay, so let me get rid of that. Okay, sorry about that. So then this is dx plus c. So again, I can still think of this as a cosine now, times a 2, and then this will be what? A negative cosine of x, and then plus c. So it looks like when all is said and done, we get a c times a cosine of x minus a 2 cosine squared x. And that's my general solution. And again, so now we have the initial condition that y of 0 is 1, if I remember correctly. So then this will become 1 is equal to c cosine of 0 is 1. So then this is just going to be minus a 2 times 1. So when I add 2, we get that 3 is equal to c. So now we can say that our particular solution is y is equal to 3 cosine of x minus 2 cosine squared of x. And that's my particular solution. All right, so that's our little introduction here to linear ODEs, specifically the non-homogeneous version. So in the next video, we're going to look at some applications of this, and then we'll also look at how can we reduce something that's not quite in this form to be in this form. So that's what we're looking at next. All right, so I will see you next time.